Next, I want to talk about section 5.2, which is a fundamental principle of counting. So we're going to talk about the number of elements in A, our inclusion-exclusion principle, how to use Venn diagrams, this will come in handy, and then De Morgan's laws. So if S is any set, we will denote the number of elements in S by N of S. Sometimes you'll also see this if you're looking at another text or taking another course. You might sometimes see this as like bar S. And you can also call this the cardinality. I know we've got lots of fancy words in math. So the number of elements in a set can be devoted like this or with bars, and we could also call it the cardinality. So for example, if I have set 173, N of S is 3. The number of elements in S is 3. If I have the empty set, I've got 0 elements. And if I have an infinite set, I'd have infinite elements. So let's talk about the inclusion-exclusion principle. Let's let S and T be sets. Then if I take the union of those sets, the size of the union of those sets is going to be the size of S, the size of T, minus the intersection. So let's make up a quick example. Let's let S equal 1, 2, 3, 4. And let's let T equal 2, 4, 6, 8. And I want to find S union T and S intersect T. Then we'll look at their sizes and show that this inclusion-exclusion principle works. So if I were to find S intersect T, that's going to be 2 and 4. Those are the elements that they have in common. I'm going to take S union T. That's going to be all the elements in S and T, where I only list the duplicates once. So I'm going to have 1, 2, 3, 4, 6, 8. So let's see. I know that the size of S is 1, 2, 3, 4. The size of T is 4. S intersect T, the size of S intersect T is 2. And the size of S union T is 6. So we can see if we look at this equation up here, I have 6. I'm going to rewrite this in a different color. I have 6 equals 4 plus 4 minus 2. And the reason I'm counting the intersection, right, is because if I didn't subtract the intersection, I would have counted 2 and 4 each twice. So, in the year 2000, Executive Magazine surveyed the presidents of the 500 largest corporations in the U.S. Of these 500 businesses, 310 people had degrees of any sort in business. 238 had undergraduate degrees in business, and 184 had graduate degrees in business. How many presidents had both undergraduate and graduate degrees in business? So now I'm looking for the intersection. So I know that the size of S union T is the size of S plus the size of T minus the size of their intersection. I'm told that 238 have an undergrad degree in business, 184 had a graduate degree in business, and I have 310 who have a business degree of any sort. That's going to be S union T. So I have 310 equals 238 plus 184 minus the intersection. So we can go ahead and solve for this. So that gives me 310 equals 422 minus the size of the intersection. I can subtract 422 from each side. That gives me 112 equals in S intersect T, where S intersect T is those with degrees with undergraduate and graduate degrees in business. A Venn diagram is a drawing that would represent these sets geometrically. To construct a Venn diagram, you draw a rectangle and view its points as all the elements in U. You then draw a circle inside the rectangle for each set, and the circles should overlap as long as they aren't disjoint, right? So their intersection wouldn't be the empty set. And we view the points in the circles as elements of each set. So you're going to have a Venn diagram. Here's your universal set. You're going to have two sets who overlap. So just like in the last example, we had 112 in the middle for S and T. Here's an example of unions and intersections and complements represented with Venn diagrams. So here I have a union B, a intersect B, and a lot of their complements. So let's draw a Venn diagram with these three sets and shade the area that represents each of these. So I might have to draw my Venn diagram a couple times. So now I have three. When I have three intersecting, it's a little bit different. So I've got one, I'll call this R, two, oh, now it's not the same size, three, okay? So T, let's label our elements. So all this is just T, right? This is T intersect R, this is R intersect S, this is T intersect S, and this is R intersect S intersect T. This is where they all overlap. So in orange, R intersect T is this area in the center right here. Now if I wanted to know R union S union T, I'm going to go ahead and shade that, and yeah, we're going to do pink. There we go. That's going to be everything in T and everything in R and everything in S, right? It's the whole kit and caboodle. This is actually kind of fun to draw on. Okay, next I want S intersect R complement intersect T complement. So this is everything not in, this is everything that's in S, R complement, and T complement. Let's take a look at what this looks like. We're going to go with yellow. Okay, so remember that T complement is everything not in T. So that's going to be all of this, right? Like everything not in T. It's going to be all of this. So that's T complement. This is getting very colorful. R complement is everything not in R. So that's all of this. Everything not in R. Sorry, not in R. And then S is just all of S. So what's our area going to look like? It's going to look like where, well, now it's kind of brown. Well, where I have the green, blue, and yellow, which is this area right here. This is S intersect R prime. Oh, why is it going underneath? Okay, so this area right here is, it's going to show up, I swear. There. Maybe not. Well, it's this shape right here. Perfect. So let's let S and T be sets. Then S union T is the same as the complement of S intersecting the complement of T. And the same thing is true for the complement of S intersect T. That's S complement T union T prime. So i.e., to form the complement of a union or intersection, you form the complements of their individual sets and change the unions to intersections or the intersections to unions. So let's prove De Morgan's law real quick. All right, so S union T, maybe I should label S and T, right? So like this is S, this is T. S union T is going to be all of this, right? This is S union T. But I don't want S union T. I want S union T complement. So S union T complement is going to be everything out here. Everything outside of S and outside of T. It's going to be all this beautiful space right here. So keep this image of the yellow space, right, in your mind as I prove it the other direction. But first thing I want to do is clear all pin markings so we don't have such a messy space. So next I'm going to take a look at S prime and T prime. So S prime is everything not in S. So it's going to be all of this. And I definitely suggest you sketch these out to get a better feeling for it. So it's going to be all of this, everything not in S. And T prime is going to be everything not in T. So it's going to be all of this, everything over here. So what I need to look at is where I have orange scribbles and green scribbles. And that's going to be in this area here, which is the same as what I had graphed earlier. The same thing is true for intersections, and I urge you to prove that to yourself.